Hello there. We're going to start a series here in astronomy covering some fundamental topics. And we're going to do a series on astronomical measurements. Fundamental stuff if you're going to want to learn about the cosmos and apply some of the main principles and measurements to grasping the vastness and the size of the cosmos and all the bodies in there. So we're going to start with numbers and units, and then we're going to continue with a few other astronomical measurement topics after this video clip. So in order to get comfortable with astronomy and some of the data and the reading and the subject matter that you run across, you need to be comfortable with very, very large numbers. And there's a lot of big numbers in astronomy because the cosmos is very, very big. So let's wrap our minds around some astronomical numbers to begin with. So astronomical numbers, what we want is representations large numbers, okay? So on a daily scale, we are used to average-sized objects, but when we start talking about the size of the Earth, the size of the Sun, the mass of the Sun, the distance to the Sun, the distance to the outer planets, the distance beyond our solar system, the distance to the nearest stars, we have to start wrapping our mind around really, really big numbers. Okay, so what we do is we use scientific notation to express these numbers. So scientific notation, this is a tool we use to express very small numbers used to express very small and very large numbers via powers of 10. So we're going to have a little template for scientific notation, and it's very important that you're able to read these numbers. So what happens is we put a non-zero digit, one non-zero digit, in front of the decimal, okay? So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. Either one of those will go there. And then we use the other digits we put behind the decimals. Okay, the other parts of the number behind the decimal. So we call them significant figures depending upon how accurately they're measured. So that's another topic of trying to figure out what your significant figures are. So typically you'll see these. You'll see a number from 1 through 9 here, and then you'll see a few other digits here. But the important part for us is to understand how this times 10 to the factor works. So for very small numbers, we'll say times 10 to the negative. So this will be a negative exponent for small numbers, okay? And then this will be a positive for large numbers. Okay, so let me give you some examples. Some examples, and there's many, many, many. Let's see, a small number, such as 0.031, we could express as, in scientific notation, I take my decimal point and I move it to the first non-zero digit and put it behind it. And this is equivalent to saying 3.1 times 10. And this is a small number that I made bigger by moving the decimal places by 1, 2, 3 spots. So it'll be times 10 to the 3. But since it's a small number and the original is digits behind the decimal, I will put a negative here. Okay? So that means it's 3 places in front of that 3. Okay, that's how I'd express that small number. A large number such as 1,473, I could express as 1.473. So there's an understood decimal place here, and I move it back 1, 2, 3 places to make it smaller. So I change 1,473 to 1.473, and I put my placeholder in terms of times 10. I say times 10 to the power of 3. I moved it 3 units. Okay? And of course, we could get much larger than this number. So some examples. Let's give you some examples of small numbers. So when we're talking about things on a very small scale, let's say the mass of an electron, the mass of a proton, the sizes of atoms, really, really small increments of time. We're talking about very, very small numbers. So here's some examples, like the mass of an electron. If we were to break apart an atom and try to figure out the mass of one of these whizzing around electrons in there, okay, we would find, this is our notation for the mass of electron, is approximately, and these can be looked up, I don't have these memorized, so 9.1 times 10 to the minus 31 kilograms. That's really, really small. So it takes a lot of electrons to make up 1 kilogram. So if you were to write this out in decimal form, you would see the utility of scientific notation. This would be like 0. If I move this decimal, let's see, 9.1, I go 1, 2, 3, 4, 5. You could see that would be tedious. You move this 31 places, and that's how that number is represented in scientific notation, because you could see it's very easy to lose your places, you know. Much easier to say 9.1 times 10 to the minus 31 kilograms than it is to say 0.000000000 and go on 31 times 9.1. Okay. Another one, mass of a proton. It's a little heavier. This is in the center of atoms. Okay. Mass of a proton, like protons that smash together inside our star, the sun, to make the energy, is really small, but it's a little heavier than the mass of an electron. This number is 1.67 times 10 to the minus 27 kilograms. So you can see a proton is really, really small amount of mass, okay, but it's obviously a little heavier than an electron. And then what else do we have? We have something called the Planck time. I really like this one. It's the smallest increment of time possible. We have a symbol for that, T sub P. These are subs. Okay. And it's approximately, what do we have? 5.391 times 10 to the minus 44 seconds. Wow, that's fast. Okay. So here's some examples of small numbers. But even more important is the big numbers that we use in astronomy. So let's take a look at some of those numbers. can start with one that comes up in a lot of astronomy, the speed of light, otherwise known as electromagnetic radiation. So Wi-Fi signals, radio signals, ultraviolet light, infrared, microwave light, those microwaves you use to heat up your food, and visible light that we see coming from the sun and reflected off objects all travel at this speed in a vacuum. So the speed of light, and I'm going to say in a vacuum, uses the symbol C, and C is approximately, I'm going to round off a little bit here, very close to 3 times 10 to the power of 8 meters every second. It's really fast. The ultimate cosmic speed limit of all the objects in the universe. Nothing travels faster than the speed of light. Okay, so we use scientific notation a lot to represent that number. Okay, and then if we go around and we start looking at the sizes of objects, let's say in our solar system and beyond, like what's the mass of the sun? The mass is heavy, really heavy. So the mass of the sun is approximately and you can look these up easily. There's so many tables online. Wikipedia tends to have pretty accurate information as far as these facts. But the mass of the sun, sometimes it's ms, or they'll use a little symbol for the sun. 2 times 10 to the 30th kilogram. That's heavy. Now, for perspective, in comparison, the mass of the Earth, which is a lot less, sometimes I just put an E on there, is 6 times 10 to the 24 kilograms. Okay, 6 places different. So you could fit a lot of teaspoons of Earth, a lot more teaspoons of Earth into the sun. I shouldn't say teaspoons because it's obviously a lot larger. So if you could take the mass of the Earth and then multiply it by a factor, you'll get the mass of the sun. Okay, so those are some big numbers. And then we tend to use distance a lot. Do a separate clip on distance. The distance average Earth-Sun. We have a unit we'll talk about that covers this, 1 AU, and that's approximately, on average, what do we have? 1.5 times 10 to the 8 kilometers. That's mind-boggling. So when you think about being on the equator and going around the entire circumference from the equator, that's almost 7,000 kilometers. It's like just over 6,700 kilometers. Okay, so, and that's just a rough estimate. So I have to look up the specific number, but that's a lot less than this number. That's a huge distance to the sun. And that is why we say on average it takes about 8 minutes for sunlight to reach the Earth. So distance is really large. Now that's just Earth-Sun distance. Now when we go further than that, the kilometers, the powers get much larger, right? We're going to have higher exponents here. So if we were talking about going to the nearest star, we're saying, 4 light years, which is a lot more kilometers away. And then we start getting into even larger units of light years. If we go and look at the observable universe, the distance, let's say, or the size, distance size of the observable universe, okay, and this is a diameter, in terms of diameter, which is the distance across through the center of a circle from one side to another, 2 radii. So this distance is approximately 93 billion, and we'll talk about this unit, light years across. huge. And what we mean by the observable universe is all the things that we could see from our standpoint. Okay, that's the furthest distance that we're able to see and collect the light. There's still more universe beyond that, but that's the limit of observation, so to speak. Very interesting topic. But we get into big, big numbers, and we could just, make lists of these, as you will see in any astronomy text. There's lots of numbers, lots of really big numbers. Okay, so when we're doing scientific notation, the rules of multiplication apply. So if I wanted to find out how many Earths will fit into the sun, I would multiply by some number and then just carry my powers of 10. Remember, multiplication can be done in any order. And the same goes for division. So if I wanted to multiply these two numbers, I'd multiply these two and then multiply my powers of 10 and use my rules of exponents and add those numbers. So the next step is, once we wrap our mind around how to represent really large numbers in astronomy, the big next step is the units. Okay, in order to communicate and share data in astronomy, it is important to use the same sort of agreements on measurement units. So what we have to do is rely upon a standard system. So if we make observations, let's say in the night sky, we need to be able to say, okay, my meter is the same as your meter. My AU is the same as your AU. And what's it all based on? My measurement of time is the same as your measurement of time. So astronomy, just like all the other sciences, rely on the SI unit standards in the metric system. So what happens is we use the metric system, and if units are not in the metric system, we do conversions to put them inside the metric system. But the SI units of standard are defined worldwide, and they're the base units we use for all the other measurements that we make. So we have in the SI system, we have 7 base units in which everything else, all the other units, are based on. And again, this is used for all disciplines, not just astronomy. So again, this is important to communicate our measurements with. So the SI system has 7 base units, and the metric system which uses those base units are powers of 10 that we use to do our conversions in between. So what are these base units? These base units are fundamental units, and you could look up how these are defined. You could go to the NIST website. NIST is the National Institute of Standards and Technology, and we have groups of scientists always working on updating how we define a measurement of length, how we define a measurement of time, how we define a measurement of mass, etc. So there's 7 base units. For us, we have the main ones will be the unit of time, length, and mass. But these 7 base units, I'll say, are for length. Okay, we have the unit, we need to define a standard for length. We will have a unit for time. We'll have a unit for mass, temperature, electric current, and then we're going to have one for luminosity, and I'm missing one more: temperature, current, luminosity, and some of these other ones are not. Oh, the amount of substance. If you've done chemistry, you've probably heard of that one. Okay, so here's our 7 base units. So how do we agree upon length? Well, the agreed upon measurement that we use use to base things like the speed of light on, etc. Or other is the meter, 1 meter. Time is 1 second. We have a standard for the second. Okay. For mass, we have a standard for the kilogram. Temperature, our standard is Kelvin, where 0 Kelvin is absolute zero, the coldest temperature possible. Current, we have the ampere. Luminosity, we have the candela. And the amount of substance, we have the mole. Okay, let's take a look up for these for a second. Now, length is going to be extremely important in astronomy because that units we use to define our larger units of measure across the solar system, across our galaxy, and further out beyond. Length standard is 1 meter. What is 1 meter? Well, you can pull up a meter stick in any standard science lab, or you may maybe found one of these. You could even print these out on your own. You could print out smaller versions and then make 1 meter out of it, or make your own meter stick, measure out 1 meter on a stick. But obviously this is not precise, right? You know, there's little fractions that might not make this exactly 1 meter. You know, maybe it's got worn down with time and that meter slowly eroded to, you know, 0.9999th of a meter. So, but this is typically what a meter looks like, okay? And this is our standard for length. And we can see that, well, if you're traveling from one city to another, it probably takes quite a few of these, and 1 meter might not be the best measure. We might want to use one of the prefixes like the kilometer to define that distance, and so on. Okay, so what is 1 meter? Well, this is defined as the length covered by light as it travels the speed of light in a vacuum, okay, in a fraction of a time period. So length, we could say, is the distance covered by light in light traveling the speed of light traveling at the speed of light c in approximately 1/3 times 10 to the 8th of a second. Okay, so remember before I said speed of light is approximately 3 times 10 to the 8th meters every second? Well, this is kind of comes back to how a meter is defined. So ordinarily you can't see this speed, right? 1 second goes by really fast, or this fraction of a second. 1 second we know goes by really fast, so this fraction of a second, 1/3 times 10 to the 8th second. So again, this is 1 2 3 4 5 6 7, and then I'm going to need one more 0 there. That's why I like scientific notation so much better, me and many others. Okay, that's 1/300 millionth of a second. Okay, so let me make sure I get all my zeros there. So it's a very small unit of time. So that's that distance. So if light was traveling at its speed, it would make, in that portion of time, it would cover a meter. So very, very precise measurement. So we know in general light is really, really fast. And here I have green laser light. Okay, you can't see it moving across this room, I'm sure, on camera. But you might be able to see it traveling through acrylic or glass. Now, it does slow down when it travels through a different medium, so you have to be careful. So it is a little slower traveling through water or glass or even air, but air is very close to a vacuum. But here you can see that, right? So I'm sure you can't see. If I were to have a piece of glass the size of a meter, you still wouldn't be able to see the difference from one end to the other. So light travels very, very quickly. Okay, so that's how we define 1 meter. And then if we go on and we look at, okay, what's our time standard? Well, we define that as 1 second, and that is a little more complex. It's based on an atomic clock, and what happens is we look at the cesium-133 atom, and as it goes between 2 hyperfine states, so it's the light, the frequency or the wavelength of the light is going back and forth between 2 states over 9 billion times. So when it goes through that amount of oscillations, we call that 1 second. So it's a little trickier, and you can look this up to get the more formal description. 1 second, which I'll denote by 1s, just like here, 1 meter, the notation is 1m, is, we could say, roughly the number of periods, oscillations, or you could say the frequency, how many waves pass by in a certain amount, in a certain increment, the number of periods, oscillations, we could say between of light transitioning between 2 levels of the cesium-133 atom. Okay, so this is what we mean by atomic clock. And I'm not going to give you the number. I mean, I guess it's out there, but it's over 9 billion oscillations. Well, let me go ahead and give you that number. I do like to be exact, but I'm going to transcribe it here. I don't have this one memorized either. 9,192,631,770 cycles. So that's how many wavelengths go back and forth, back and forth, back and forth in what we define as 1 second. So there is some upgrades they're trying to make on this. So this is the atomic clock, upgrades. Well, there's many a scientist still working on making even more precise definition for a second. But you have to think of, historically, this is quite a feat, because historically it was based on the Earth and the rotation of the Earth. So we know a day is approximately 24 hours. That's not exactly exact, right? So we could say 24 hours, and then we divide it up into minutes and seconds. So we could define our second based on that 24-hour day. But that's not exact, in that the Earth's rotation about its axis has changed over time. The period of a day was much shorter back in the dinosaur times, and it's changed significantly. And it has to do with the moon pulling on the Earth and the Earth pulling back on the moon. So there's a little changes in the rotation rates from that, from angular momentum conservation. Now, other things that could change that as well are, you get an earthquake that happens and it shifts the mass of the Earth. So that would also change the rotation or the spin rate of the Earth. So that's not entirely accurate in that sense as well. So we needed something a little more concrete and fundamental, And the other types of clocks that we had before were water clocks. We used to use candles, but also pendulums. And I'm looking for pendulum, a simple pendulum. So we have old-fashioned pendulum clocks that had to be wound up over time, but they were hard to keep track of too. Over time, this slows, right? It's not a perfect system to have a pendulum clock and base your second on that. So obviously this needs really sophisticated lab equipment to be able to communicate this idea of a second, but it's the best, most accurate clock we have so far. Okay, that's the time standard. Now let's go back here and look at our kilogram standard. Okay, the mass standard is the kilogram. This is the only base unit of the 7 that requires a prefix. It's not gram, it's kilogram, where 1,000 grams equal 1 kilogram. That K in front of the G is a prefix right here, which we'll look over real quick when we end this short. Okay, so 1 kilogram this has just changed recently, so a year, 2 years ago. So a kilogram used to be defined as being this value, the mass of this lump of iridium platinum in a vault in France, but it had problems because it would lose a bit of mass over time. So now this is even more sophisticated. This is an increment, incremental value of the Planck constant in a joule per second. Joule is a measure of energy per second. Incremental value of the Planck constant in joules per second, and it's really based on quantum mechanical principles. So don't worry if you don't understand this. Just know that it's based on this fundamental idea of something called the Planck constant and transition frequencies. And the speed of light. Okay, so it's based on quantum mechanical principles that are a little difficult to go over. You have to really go through, what Planck constant is and what are some of these properties of atomic transition that this kilogram is based on. So it starts to get really complicated. So a kilogram, a good way to think of it, is approximately equal to 1 liter of water. So here I have a beaker which is filled up to 500 milliliters. Okay, so if I had 2 of these filled, that would be approximately 1 kilogram if I took away the mass of the beaker. Okay, so that is what they used to want to define 1 kilogram to be, but it was slightly off. So historically, we would say 1 kilogram was approximately equal to 1 liter of water, H2O. Okay, a little slightly off. It was a mass equivalent. They had a measured out cylinder in a vault. the National Bureaus of Standards. So instead of these two, this right here is a lump of metal. This is 500 grams and this is 500 grams. So together these two are 1 kilogram. Maybe you have masses for working out. So, you'll see, 5 kilogram, they call them weights, but weight and mass are not the same thing. You'll have 5 kilograms, 1 kilogram. You could read a few products to get your mind around what 1 kilogram is. Okay, and here is another set that makes up 1 kilogram of mass that we use in lab. So we have a bunch of these that we can adjust to make 1 kilogram out of. So there's a lot of history that goes behind what 1 kilogram is. So it's a lot easier to understand than in terms of quantum mechanics, but know that we have that precisely defined. So what we have is something that you have to always remember, and I will just make a note. Mass is not equal to weight. And in astronomy, we use kilograms. And I know one of the habits we do on a daily basis is we say pounds. That's a 5-pound bag of potatoes instead of saying it's kilogram equivalent. Now, the danger there is that mass is measured in kilograms. It's the amount of substance that you have. But weight is force. So mass is different than, this is force based on gravity. And mass is what we say is precisely what we're saying. We're like how much of those atoms packed in a certain amount of space, how much does that make in terms of a kilogram? It's an intrinsic property of a material. Okay? So on Earth, we can say 1 kilogram is approximately equal to 2.2 pounds. If we use the imperial units. The only problem with that is, okay, I have this 2.2 pound bag of potatoes, which is equal to 1 kilogram. I go to the moon, and guess what? It's not going to be 2.2 pounds anymore. It'd still be 1 kilogram bag of potatoes. However, now it's going to be maybe 1 pound less than 1 pound. If I took that bag of potatoes to the planet Mars, which again will have a different amount of gravity acting on its surface. Mars is less massive than the Earth by about 1/3, so it has less force of gravity acting on it. So it'll be about 1/3 less in terms of pounds. So if I took that 1 kilogram bag to Mars, it'll be again less than 2.2 pounds. So this is the problem with using some of these units like pounds here. That's a measure of force. Okay? But roughly people do make these unit conversions a lot. So just know, so on Earth only can you get away with that as an approximation. Mass and weight, not the same thing. Okay, let's take a look at one more of these units, temperature. Okay, we covered the 3 fundamental units that are used pretty much to define everything else. Well, we can make most of our measurements in terms of the meter, the second, the kilogram. And we can look at like energy, units of energy based on those, and so much more. But moving on, one more important one that does come up as far as astronomy goes is temperature. And we do compare temperatures of objects. So really important, we use a scientific scale of measure for temperature called Kelvin, symbol K. Okay, so absolute 0 is 0 Kelvin. We say this is the lowest possible temperature to be measured. Okay, so things are not, they erroneously sometimes say things are not moving, but things are always moving. So 0 K is like the coldest that we have. And this is temperature is a measure of the heat and the energy contained in an object or system. Now 0 Kelvin is equivalent to minus 273.15 degrees Celsius. this is another scale that we use in the metric system. So Celsius is based on water, boiling, and freezing point of water. So, degrees Celsius, we're familiar with, we say 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius is the boiling point of water. But again, this is at standard conditions. So standard atmospheric pressure on Earth, so pressure could change things. If we try to boil water on the surface of the Earth at sea level versus on top of a very high mountain like Mount Everest, this number would not be exact, it would change. So that's a very interesting thought to keep in mind. So this is at standard conditions. There's so much in science. Now this is equivalent, we could take any, there's a formula that goes between degrees Celsius and degrees Fahrenheit, which is the system that we use. Typically you'll say, oh, it's like 85 degrees Fahrenheit outside, or it's 65 degrees Fahrenheit. This is the one we're used to, and based on imperial units. So it can be a little tricky going back and forth. Okay, I have a little bit of a basis of it because I grew up with Celsius, so we know 0 degrees Celsius is like 32 degrees Fahrenheit, so you can make those conversions. If the gap gets a little bigger as you get towards 0 Kelvin. Okay, so we know 273 Kelvin is close to that 0 degrees Celsius that we have right there. So when we talk about temperatures of stars, we're talking about the center of our sun is millions of degrees Fahrenheit, millions of degrees Celsius, they're not too far away, millions of degrees Kelvin. So the scale of only a difference of 300 doesn't factor in that much of a difference when you're talking about the interior temperatures of stars. But if we were to talk about like what's the temperature out in space, so if we were to get in our spaceship and go out to the asteroid belt and float around there a little bit, what's the average temperature out there? It's about 3 Kelvin. It's very cold. Okay, and you'll see that scale used a lot. Okay, let's do some conversions to become familiar with how we use these units. Okay, now that we understand where some of these fundamental units come from, it's important to know how to do standard conversions, going back and forth from metric prefixes, or go back and forth from imperial units to SI units, etc. Doing your unit conversions correctly is really important. There has been known spacecraft lost, airplane crashes due to bad unit conversions. So one example is the Mars Climate Orbiter. This is 1999, and it crashed near the surface of the planet because it came in too close to the surface. And it was all because we had Lockheed Martin and NASA, and the two of them incorrectly communicated units. One was using imperial, one was using the metric system. So anyway, it's very important to learn how to convert. Conversions we apply. So we apply dimensional analysis when we're doing unit conversions. And the idea is to, if you have a certain unit, like you have a foot, and you want to go to a meter, you want to get rid of the feet and introduce the meter. So you have to know the conversion values. And these are easy to look up. I know on my own quizzes and tests, I provide those. I don't expect anyone to memorize those. So you're given those factors, but you have to know how to go back and forth. That's the important part. Let's start with the SI prefixes. So first, SI prefixes. These are the powers of 10 that we use within the metric system. Very important to know how to go back and forth. And very important to know how to use the appropriate measure. Like when do we use a millimeter? When do we use a centimeter? When do we use a meter? When do we use a kilometer? When do we use a megameter? So small objects will use the smaller little divisions. Larger objects, about meter stick size, will use the meter values. And even larger than that, we'll use the kilometers. So important to make these. So for SI prefixes, let's see. Let's look at some length examples. Let's say I had 5,321 centimeters, okay? And I want to know how many meters that is. Maybe I want to know how many kilometers that is. Maybe I want to know how many millimeters that is, etc. The nice thing about the prefixes is they're all by powers of 10, and you could look these up. So a centimeter is much smaller increment than a meter. There's 100 centimeters that make up a meter, okay, in a meter stick. And each of those centimeters are even smaller. You could take a centimeter, which is about this big right here, and you could break it down into 10 more pieces, each of those pieces being a millimeter. So it's important to, when you're doing these conversions, to know what the factors are. So 1 centimeter, I'm going to go this way. My brain works better with this conversion. 100 centimeters is equal to 1 meter. Okay. What we know is 10 centimeters, or I can even go to 1,000 centimeters, millimeters, is equal to 1 meter. So if I divide that further into 10 units, I get the millimeter. And then what about a kilometer? Well, what I know is that 1 kilometer is equal to 0.001 meters, or 1,000 meters equals 1 kilometer, whichever you remember. Okay. There's many more. There's like decimeters, there's hectometers, megameters. So you can look up all the prefixes. These are some of the ones that are most used. So how do we do these conversions? Let's do a sample set here. We have 5,321 centimeters. We want to know how many meters that is. We use the fact that 100 centimeters equal 1 meter. So I'm going to say 5,321 centimeters, and I'm going to multiply by the factor that will get rid of the centimeters and introduce the meters. So the important part here is to recognize this is over 1, and 5,321 centimeters, what I do is I divide by 100 centimeters, and I should say, it's another way of saying divide by 100 centimeters, but the way I'll think of it here is multiply by 1 over 100, where 1 meter is equivalent to 100 centimeters. So notice what happens here. I always know how to arrange these because the idea is to get rid of the centimeter value, whoops, and introduce the meter value. That's how I typically do my conversion. Sometimes you're going to multiply by many factors across until you get your desired unit. So here I end up with powers of 10, you're just moving the decimal place. So this will be 5, 3, 2, 1. I go over 2 places, so this is 5.53.21 meters. Okay. And that's how that works. Now, what about 5,321 centimeters equals how many kilometers? I could say, I could go further, I could go with what I have, 53.21 meters times, I'm going to skip the one step, I could do this previous step and go centimeters to meters and then meters to kilometers. I'll just sort of adopt my answer from previously. So 53.21 meters times, I know that I have 1,000 meters in 1 kilometer. Or I could say 1 meter in 0.001 kilometers. Either one will still work. And that will give me a value of, go back 1, 2, 3 places, so 0.05321, and that will be kilometers, because as you can see, the way I multiply my factor is to have this over 1, get rid of my meters, introduce my kilometers, and that's my value in kilometers. Now what about converting to millimeters? Well, now I probably want to go back to my centimeter value and say, goes how many millimeters? Okay, well this one I'm going to do, I'm going to multiply by, we have 1, we know there's 10 centimeters in 10 millimeters in 1 centimeter. So let me see, I want to get rid of my centimeters, so I'll say 1 centimeter is equivalent to 10 millimeters. So since a centimeter is a larger measure of unit, right, we're going to have a lot more millimeters to fill that space. And that will give me a value of 53,210 millimeters. Okay. It's a smaller unit of measure, so we're going to need a lot more of them to make that space up. And the idea again was, okay, what do I need to get rid of, and what do I want to introduce here? Okay. So notice these need to match up. Get meters to get meters. Cancel these out, cancel these out to get kilometers, cancel these out to get millimeters. And that's how it works. And then the big thing is okay, when you're using metric prefixes, which is the most appropriate one that you use for this measure? What's the most appropriate measure for 5,321 centimeters? So I look at this and I say, well, 53.21 meters, oh, that's a good way of representing it. This is really a little wonky, 0.05321 kilometers, that's a little rough. 53,210 millimeters, well, I'm adding more digits, and you tend to lose a lot of digits if you have many of them, so it's easier to stick with the simplest number. So the best representation here would probably be to say, using meters, to say 53.21 meters. So really important. Now, I only use the metric prefixes here for length. But the same goes, you could say centigrams, so centigrams to grams, and you could say grams, centigrams to kilograms, and you could also say centigrams to milligrams. So we use milligrams, kilograms, grams. We convert between those prefixes a lot, and also for seconds too. You could have nanoseconds, which are really, really tiny measures, milliseconds, kiloseconds, etc. So a lot of good prefixes to work with. Now to do conversions outside the metric system, let's look at imperial units. Okay, doing our imperial to metric, metric to imperial conversions, really important. As I mentioned earlier, it could lead to catastrophic results. So good measures gone bad is not what we want here. So we want to be able to convert between the imperial units like feet, inches, miles, to the metric system like kilometers, meters, etc. and also some of the other base units that are used. Okay, here's an example. How do we convert 372 feet to meters? What we have to do is employ our knowledge or look it up in a table of what the conversion for feet to meters is. So our standard is, how many feet are there in a meter, or how many meters are there in a foot? Well, here we use the fact that we look these up. 1 feet is equal to 0.3048 meters. Some people like to memorize those, but there's so many numbers, so it's easy enough to look up. Other things that you have to remember might be more important. So 1 foot is equivalent to this amount of meters. So a foot is much smaller than a meter. So we can at least fit 3 feet inside a meter stick if you look at that scale. Okay, so we're looking at a partial amount of the meter stick here. And what we're going to do is we're going to take that 372 feet. We want to get rid of it, so we want to multiply by our foot in the denominator, our meters in the numerator, get rid of our feet, and introduce the meter. So I'm going to use my conversion of 0.3048 here, which is equivalent to 1 foot, and this will ensure that I will get rid of my feet and introduce the meter, and I will get a value in terms of meters, which is, what do we have here? If you multiply this, 372 times 0.3048, you should get 113, and you round that off, 0.3856. So depending upon how many significant figures you want to use, or rounding off to the nearest tenth, etc., whatever is expressed in the problem, okay, or necessary in the problem that you're doing. And so that's how many meters we had. As expected, a lot less. Okay, some other examples here. Let's go ahead and do miles to kilometers, or kilometers to miles. So especially when we're navigating into closer bodies in our solar system, you know, we say the sun is so many million miles away, or the moon is so many miles away, or it's so many kilometers away. We want to go back and forth between those units. So here what I want to know is what my miles to kilometer conversion is. So if I look this up, I'll get the handy fact that 1 mile, sometimes denoted as MIL, is approximately equivalent to 1.6 kilometers. Okay, so to do this conversion, I'm going to go, well, this is going to be 625 miles times 1 mile, which is what I want to get rid of here, and put my kilometers on top, because I want to introduce the kilometer unit to use. And that is equivalent to, let's see, 1.6 times 625. I multiply those numbers out, and I get approximately 1,000 kilometers out of that. These cancel, and this is my end unit. Okay. So one thing to notice, well, maybe I want to know how many meters this is, or how many megameters this is. Now, a megameter is times 10 to the power 6 meters. A kilometer is times 10 to the 3 meters. So this is equivalent to 1 megameter. Now, if I needed to, I could add more than one conversion factor. If I wanted to go to the value of, let's say, I want to figure out how many meters that is, I could back up and I could say, my answer here, I could go ahead and say, well, let me go a little further with this, and I'd like to know what the units are in terms of meters. And I'd say, well, there's 1 kilometer for every 1,000 meters. Okay? And I'd further get rid of this, and I would get an answer of 1 times 10 to the 6th meters, 3 extra places. Okay? So you could keep multiplying by conversion factors, as many as you need to get to your end result. Let's do another one here. let's go from, let's say, kilometers to miles. Let's say I had 25 kilometers. Typical city to city distance equals how many miles? Well, we could say, again, we could use this conversion. We could say 25 kilometers times, there's 1.6 kilometer for every mile. And I want to get rid of my kilometer units, introduce the mile units, and I get the value of 15.625. That makes sense because a mile is a bigger measure than a kilometer. So if you've ever run a race, a 5K race or a 5K walk, 5K is a lot more, the kilometer measure, it's going to be a larger number because a kilometer measure is a smaller one than a mile. Mile is a larger distance than a kilometer. Okay, so really important that you know how to do this, and then you could go on. You could convert this to other values you need. So there's no limit on how many factors you multiply to get to your end result. And this applies not just to lengths. You know, you could easily go, you could do like kilograms to grams. You could do other types of units that you have, let's say calories. If you need to convert calories to joules, then those are both units of energy. You could also use this system, etc. Now, one important fundamental idea is this. A lot of times when we're solving problems in science, it really helps to understand how to do unit conversions to come to the desired result. Sometimes we know what kind of unit we want in our end answer, and that will help us solve the problems by knowing how to formulate that unit. So it's sort of like a backdoor method to solving problems. We'll say, how do I make this unit? What do I need to do to make this unit? What are the multiplication factors, the conversion factors involved? And you could play around with those, and you have this, these are the units you have, this is the unit you want, what are the steps in between to get that unit that you want? So unit conversions play a huge role in science and give you a lot of insight into what the problem's about, what the idea is about, what the fundamentals that you're studying are about, and how to put those together. So units are fundamental. You can't get away from them, and they're very fascinating in looking at the history of their definition and how we define them today. There's a lot of extreme science involved in those. All right.